We are starting our last chapter of the course, and this is on gases. So today we're going to talk about properties of gases. Gases are all around us. We're surrounded by gases. This is a common topic that's covered in introductory chemistry courses. So we have a couple different types of gases. We have elements that exist as gases at room temperature. These are like hydrogen, nitrogen, oxygen, fluorine, chlorine, and the noble gases. And you're familiar with a lot of these. We also have non-metal oxides, including carbon monoxide, carbon dioxide, nitrogen monoxide, and so on. And so these are just different, types of gases. We have elemental gases, and then we have gases that are compounds. The behavior of gases is really different from liquids and solids, which is why gases get their own chapter apart from liquids and solids. Liquids and solids react and behave fairly similarly to each other, but gases is a whole different kind of beast. So these gas particles are much farther apart than particles in a liquid or a solid. We talked about intermolecular forces previously. These gas particles have overcome the intermolecular forces that are keeping them in place in liquids or solids, and now are able to move freely. Gases have no definite shape, no definite volume. They will always fill any container. If you have a gas like sulfur dioxide, smells like rotten eggs, and we released it in part of the classroom, well, then that sulfur dioxide will expand and fill the container, which in this case would be our classroom, until it's spread uniformly throughout, which means we would be able to smell it all across the classroom. So that's the whole no definite shape, right? Gases don't have a specific shape, whereas like a solid does. A solid is shaped like, a chair or a table. And gases don't have a definite volume, which means that they can be compressed or they can expand. So they'll always take the shape and volume of whatever container you put them in. And then gases are less dense than solids or liquids. We've talked about density with respect to solids or liquids. Most times for solids, we report this as grams per centimeter cubed. And for liquids, a lot of times we'll report this as grams per milliliter. These are the same thing. But gases, we report them as grams per liter because they are much, much less dense. So to talk about gas behavior, we're going to go through kinetic molecular theory. And kinetic molecular theory will kind of dictate how we think about the gases. These are some really broad generalizations about gas behavior. And there are some assumptions that are made kind of within them, but this is going to govern how we talk about gases in chemistry. So the kinetic molecular theory of gases, which is often abbreviated, if you see this abbreviated as KMT, that's what it's talking about. And so the first one is that gases consist of small particles, whether they're atoms or molecules, right? So whether it's atoms like neon or molecules like maybe carbon dioxide, but the gases are small particles that move randomly with high velocities. So they're teeny tiny particles that are moving super fast, all in the, just kind of crazy all over the place, doing their own thing, with very high velocities, which means they are moving very, very quickly. Our second tenet of kinetic molecular theory is that the attractive forces between particles of a gas are usually very small. So these attractive forces, that's talking about the intermolecular forces. And these intermolecular forces between a gas are really, really small for two reasons. One, the gases are really, really far apart, right? The gas particles themselves. And so since they are not really close to each other, they're not going to experience very much of this attractive force. Also, like we just said, these gas particles are moving very, very quickly. And so even if they happen to come near each other, they're going to, pass each other, fly past each other so quickly that they're not going to have time to form these attractions. So the attractive forces between particles of a gas are usually very small. We essentially just assume that they are zero. There's no attractive forces between particles of a gas. In reality, yeah, a little bit, but it makes our calculations easier if we assume that these are zero. Our next one is that the actual volume occupied by gas molecules is very small compared to the volume that the gas occupies. So what this means is that if we think about our classroom, right? In our classroom, we have, oxygen, we have carbon dioxide, we have nitrogen, and they're filling the room, right? Because gases will expand to fill whatever container you put them in. But the gas particles themselves are very, very, very tiny, right? Molecules and atoms are really, really small. So the volume occupied by the gas particles themselves is very small compared to the volume the gas occupies, like the classroom. And so we will essentially say that the volume that the gas particles occupy, again, instead of thinking this is very small, we're going to say this is essentially 0 because it is so, so small. So the gas particles themselves kind of say that they have a 0 volume with respect to, a classroom or some other very large space. The gas particles are in constant motion. They are always moving, and they are moving rapidly in straight paths. And so what this means is, say there was, this is our gas, we put it in a box. And it's going to, maybe it starts here and it goes here, and then it's going to go in a straight path until it hits a wall. And then it's going to go in a straight path until it hits a wall. And again, and again, and again, right? And it's just going to keep going in straight paths until it hits a wall or until it hits another particle and bounces off. But these gas particles are always moving. They're moving rapidly, and they're moving in straight paths until they hit something and they'll bounce off of that. Then our last one, the average kinetic energy of gas molecules is proportional to the Kelvin temperature. And essentially what this means, we think about kinetic energy as the energy of motion. And so when we say that it's proportional to the Kelvin temperature, right, and that's important, not Celsius. Do not use Celsius for this entire chapter. This whole chapter, we need to do calculations in Kelvin in order to make our calculations work. So that's kind of an important distinction there. But the average kinetic energy of the gas particles is proportional to the Kelvin temperature, which means that if you increase your temperature, right, your temperature goes up, then that means that your kinetic energy goes up. And what this really ends up meaning is that when our temperature goes up, our particle velocity moves. It goes up. The particles move faster at higher temperatures. And this is going to be really important when we talk about gases. So if we increase the temperature, we are increasing the motion of the molecules. If we decrease the temperature, we are decreasing the motion of the molecules. Okay. So one of the gas properties that we are going to talk about today is pressure. We're going to talk a lot about pressure throughout this chapter. And I want you to think about pressure in a really specific way. I want you to think about pressure as collisions. Every time you hear the word pressure, I want you to think about collisions. How many collisions there are? Are there going to be more collisions if this happens, or going to be less collisions if this happens? Okay, we're all about collisions. And these collisions are when the gas particles strike the walls of the container. Okay, so that's this bit here. And so every time the gas particles hit the walls of the container, they are exerting pressure. And if we add up all of those collisions, right, all of those, striking the walls, then we will get the total pressure of the gas. So when we're thinking about pressure, we want to think about if we do something to this gas, right, we increase the temperature, decrease the temperature, change the volume, whatever we do, is that going to increase the amount of collisions or decrease the amount of collisions? Because if it increases the amount of collisions, that increases the pressure. If it decreases the amount of collisions, then it will decrease the pressure. And so it's very helpful to think about pressure through collisions. For example, if the gas is heated, right, we increase the temperature, like we were just talking about on the last slide, then that will cause the molecules to move faster. And if the molecules are moving faster, then they will hit the walls of the container more often. And so if they hit the walls of the container more often, that means we are increasing collisions, right? And if we are increasing the amount of collisions, that means we are increasing the pressure. So again, I would always think about collisions when you're thinking about pressure. And so again, down here it says the gas particles are moving in straight lines right within the container. and they'll exert pressure when they, collide with the walls. So we're all about the collisions. The opposite is also true. If I cooled down my gas, right, then my molecules would move slower. They would have less collisions, and that would cause the pressure to decrease. So we have atmospheric pressure, right? And so the atmospheric pressure is the pressure exerted, essentially, the pressure that's kind of sitting on you at all times. We don't notice it because we're used to it, because there's always atmosphere sitting on top of us, right? But there is some amount of atmospheric pressure that you feel. And if you go up, to higher elevations, there's actually less atmospheric pressure because there's literally less atmosphere sitting on top of you. This is why, cookies bake at different temperature, waters boil at different temperatures, right? Because at higher altitudes, you have a different amount of atmospheric pressure, which, causes changes. The atmospheric pressure is the pressure exerted by a column of air. So if you think about directly on top of you, there's a column of air sitting on you. And it's from the top of the atmosphere to the surface of the earth, or, we'll just say, on your head at the moment. That is the total amount of atmospheric pressure at, a given altitude. Okay. And so at sea level, which we are not, but if we were at sea level, then we consider that 1 atmospheric pressure. If you go above sea level, then you're going to have less than 1 atmosphere of pressure sitting on you. And if you go below sea level, then you would have more, than 1 atmosphere of pressure sitting on you. And then this is combined of all the molecules in the air. Over here, it's got nitrogen, oxygen, and some other things, carbon dioxide and things like that. But it's all of the pressure that is sitting on you. So at sea level, right, we have atmospheric pressure is 760 millimeters of mercury. And we are going to use that quite a bit. If we go, if you look at Los Angeles is just above sea level. Not very much, but just above. And so since it's above sea level, right, we're going up in altitude, that means there is less, atmosphere sitting on top of you. So atmospheric pressure decreases. It didn't decrease very much because we didn't change our altitude very much. But if we went up, to the top of Mount Whitney, it's a very large change in altitude. Now you're up really, really high. And so there's a lot less atmosphere sitting on top of you. So we are having a lower atmospheric pressure on top of Mount Whitney. So it depends on, like I said, if you're above or below sea level. For all of our calculations, though, in this class, we are going to assume that we are at sea level. We're not going to make any adjustments for altitude, but this is just for understanding purposes, where are these numbers coming from? So that's pressure. We're going to come back to pressure, but the 760 millimeters of mercury, so mmHg, that's going to be an important number for us. This is 1 atm. That means just one atmosphere, right? And 760 millimeters of mercury. Both of those are going to come into play later. So another property of gases that we're going to talk about today is volume. And the volume of a gas is the size of the container. We spend a lot of time in chemistry measuring, volumes of liquids mostly, not so much volumes of solids, but a lot of times we'll measure volume of liquid and we'll use a graduated cylinder or maybe a beaker or a burette or something like that. But the volume of the gas will always be equal to the size of the container that you put your gas in. And if your container can expand, and so if it's a flexible volume, when I think about flexible volumes, I always think about balloons. And I think balloons, right? Balloons are kind of our go-to, something that the volume can change. And if we add more particles, then the volume will increase. And so this would be our example here is if you were going to have a birthday party or some other kind of party and you needed to blow up some balloons, right? The way that you inflate your balloon, the way that you increase the volume is you blow it up. You literally, use your mouth and you input more particles into the balloon. And as you add more particles, your balloon gets bigger, right? And so that's that's what I would think of when we think about adding more particles. I would think about blowing up a balloon. You're inputting more gas into the balloon, which when you input more gas into the balloon, you are adding more particles, which increases the number of collisions, right? And when we increase that number of collisions, pressure builds up inside the balloon. And when pressure builds up inside the balloon, and since the balloon can expand, then the balloon will get bigger and bigger and bigger. Eventually, though, if you keep doing that, you'll build up too much pressure in your balloon and it will pop. Another way you can change the volume, right, if we have a flexible volume, is you can lower the temperature. You can actually do this at home if you have a balloon. Right, like I said, I'm always, I'm going to think about balloons with all of these. Blow up your balloon, I don't know, to a reasonable size, and then tie it off, and then put your balloon in the freezer. Okay, so if we put the balloon in the freezer, we are lowering the temperature of our gas particles, right? We are cooling them down. And when we cool down those gas particles, that causes them to move slower. And if the gas particles are moving slower, they are making less collisions with the sides of the container. And if we have less collisions, then we have less pressure. And if we have less pressure, then our balloon will shrink. So if you stick your balloon in the freezer, spoiler alert, it will shrink, which is kind of cool. And then you can take it back out, put it on your counter, and it'll expand again. But it's pretty neat. So lowering the temperature of the gas will reduce the kinetic energy of the molecules. It will make them move slower. And if we make them move slower, then that will decrease the number of collisions, which decreases the pressure, which decreases the volume. Okay? And I would follow that whole train of thought to arrive at the correct, at the correct answer. Always think about collisions. It's really going to help you out here. So temperature is another one. The temperature of a gas is related to the kinetic energy, right? And the kinetic energy we decided was the motion of the particles, or the velocity of the particles, right? How fast are they moving? And we are measuring it in Kelvin, okay? Do not use Celsius, and goodness, never use Fahrenheit. But the temperature is always going to be related to the kinetic energy. So if we cool down our gas, right, we decrease our temperature, we decrease the kinetic energy. If we increase our temperature, then we increase the kinetic energy. So it's always going to be related. They're directly related. Just make sure that your temperature is in Kelvin. This one says, for example, in a rigid container, so not a balloon, that means like a box or something that can't move. Heating a gas will increase the energy of the molecules and will therefore increase the pressure of the gas inside. So let's think about this. If we heat up our gas, right, now our gas particles are moving faster. And if our gas particles are moving faster, then they're going to make more collisions with the walls of the container. More collisions will increase the pressure of the gas inside the container. Always bring it back to collisions. And then lastly, we have this value N, which we're not going to talk much about today, but N is the amount of gas. So N you can think of as number, right? That's where we get the N, number of moles of gas. Okay, so if you see N, it's talking about, usually it's talking about moles. It's related to grams, obviously, through the molar mass, but usually we're going to use N with respect to moles. And so this one, if we add air to a bicycle tire, right, if we we are adding particles that will increase the number of, particles that are in there, which increases the number of collisions, right, which increases the pressure inside your tire. So if you add, if you're pumping up your bicycle tire, you're putting more gas particles into your tire, which makes more collisions, which results in a higher pressure inside the tire, which then allows you to ride your bike more successfully. Usually the mass of a gas is measured in grams, just in general, right? We measure most things in grams. But when we do gas law calculations, we're going to change grams into moles. So that's why I was saying earlier, that value N, we're typically going to use it as moles. It does stand for technically the amount of the gas, which is kind of ambiguous, okay, grams or moles. But most times we're going to use that as moles. So here's a bunch of our properties, right? Capital P stands for pressure. And we are going to measure that in a couple different ways. We're going to measure that in atmospheres, which is ATM, millimeters of mercury, and torr and Pascal. So we're going to talk about all of those shortly. And then capital V will be for volume. Usually that's going to be measured in liters. It's kind of uncommon that you'll see it in milliliters because gases we use large volumes most times. But it could be milliliters, but oftentimes it's liters. Temperature will be capital T, and again, we're going to use Kelvin in our calculations. So be very, very careful about that. You're always going to need to change your Celsius into Kelvin by adding 273 there. And then amount is N, lowercase n, and that's how much gas is present in your container. And again, we're pretty much going to use this as moles in our calculations, not really as grams. So I want you to go ahead and pause here and find your Chapter 11 lecture worksheet and work through problems 1 through 7. That's just going to be covering these definitions of temperature, pressure, and volume. Okay? So go ahead, pause here, and then come back when you're done. All right, moving on. So today, we're going to focus mostly on talking about pressure. We talked a little bit about it already with collisions, but we're going to look at, where does this, all these numbers come from with respect to pressure, and how can we interconvert between them. So we're going to look at some conversion factors to change, millimeters of mercury into atmospheres and things like that. So gas pressure. So this says when billions of gas particles collide with the walls of a container, they exert pressure, which is technically defined as force over area. This is not going to be a super useful definition for us in chemistry, but it is the technical definition for it. If you get into physics at any time, then you're going to define pressure as force over area. Here, like I said, a more useful definition, we're going to look at collisions mostly. But again, the collisions, collide with force over some area. So it's not like we're not using this definition. It's just not as useful for any kind of calculations. So just a little bit of history. The pressure of the air, or atmospheric pressure, is measured with a barometer, which was originally developed by Torricelli in 1643. Which you don't need to know, it's just more like fun facts. And essentially what's happening, right, is there's this pool of mercury at the bottom. This is all mercury. So you can see that this was not a recent experiment. So liquid mercury, and then what they did is they took this big tube that's standing up, and they evacuated, they put it under vacuum. So they sucked everything out. There was no, nothing in it. There's no air particles. There's no nothing. And then they stuck it upside down in the pool of mercury. Okay, so you can think about it being a test tube where this side is open and this side is closed. And they stuck it upside down. And then the way that the experiment works is that the atmosphere, right, the atmosphere is pushing down on this mercury. And when it's pushing down on the mercury, that forces some of this mercury up into the tube. And the gas in the atmosphere keeps pushing down on this tube, and the mercury keeps rising into this evacuated tube. And the height that it ended up rising was 760 millimeters. Like they literally just took a ruler or a meter stick, right? And they measured, okay, what's the top of this mercury column? And so they measured from, the start of the tube up to the top, and they said that is 760 millimeters of mercury. So they said, okay, the atmosphere, right? The atmosphere, it applies enough pressure that it causes the mercury to rise 760 millimeters of mercury. So they said, all right, one atmosphere of pressure is equal to 760 millimeters of mercury. So that's where we get those numbers from. Okay, the gases, right? So again, we had liquid mercury in the bottom. We had this test tube essentially that we sucked all of everything out. There's not even any air in there. And then we stuck it upside down in the pool of mercury. The pool of mercury or the gases in the atmosphere pressed down on the pool of mercury, and the way that it relieved that pressure was to shoot some of the mercury up into the tube. And the height that it rose is 760 millimeters of mercury. Okay, so that is how we are defining atmospheric pressure. So 1 atmosphere, or 1 ATM, is defined as exactly 760 millimeters of mercury. And this guy's name, Torricelli, right? Most times in chemistry or in, science in general, if people discover something, they name it after themselves. So he's like, all right, cool. So we're going to call this 760 millimeters of mercury, but I also want it called 760 torr for Torricelli, which is fine. So Torr and millimeters of mercury are the same thing. So if you see something asking about, right, that's this. If you see something asking about millimeters of mercury or asking about torr, they are the same thing. So 1 atmosphere is equal to 760 millimeters of mercury, which is the same thing as 760 torr. There was another guy, Pascal, who was working on this around the same time, and he came up with his own way of measuring pressure. And so we also have kilopascals. So this guy, Pascal, right, obviously he named it after himself, as we do. And he said that, okay, 1 atmosphere of pressure is equal to 101.325, which we usually just will use 101.3 kilopascals. So, in total, this is what you really need to know. 1 atmosphere of pressure is equal to 760 millimeters of mercury, which is equal to 760 torr, which is equal to 101.3 kilopascals. Because these are all equal to each other, it actually allows us to really easily convert between units. So I'm going to show you in just a second how to do that conversion. So here it is, a bunch of them. We've got all of these things. So all of these here, these are all equal to each other. And like I said, it's going to allow us to kind of do the conversions a little bit cool. So we have 1 atmosphere, 760 millimeters mercury, 760 torr. If you did inches of mercury, which is, nobody uses inches, but if you did, it's 29.9 inches of mercury, 14.7 pounds per square inch, or PSI, 101.325 pascals, or 101.325 kilopascals. So again, the ones that we're going to use are going to be are these ones. Okay. The rest of them you have access to, but again, you're not gonna use them for anything. So let's see how to do these pressure conversions. First one, what is 475 millimeters of mercury expressed in ATM? So we are going to do train tracks, right? This whole conversion thing. We're going to do some train tracks. So 475 millimeters of mercury is going to go in the beginning of my train track. Okay. And I'm going to write all of my conversion factors that I know up at the top. We had 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torr, which is equal to 101.3 kilopascals. And no, you don't need to memorize this. I will allow you to have access to this during quizzes and tests and things like that. You will likely memorize it because you're going to use it a lot, but you don't have to. So 475 millimeters of mercury. So these conversions are much easier than those that we were doing with stoichiometry and things like that. If we have millimeters of mercury in this, top left, then we know units cancel down and to the right. So we need to have millimeters of mercury down here. So we look up top and we see our conversion factors and we see what number goes with millimeters of mercury. So 760, right, is the number that goes with that unit, millimeters of mercury. And then we are trying to find atmospheres. So we're going to put atmospheres on top. And then again, we're going to go see what number up in our conversion factors goes with atmospheres. So that's a 1, right? 760 millimeters of mercury is equal to 1 atmosphere. Double check, millimeters of mercury cancels millimeters of mercury. We're left with atmospheres, which is what we want. So we can just divide that up. We get 0.63 ATMs. So don't make this too hard, okay? These are going to be really straightforward conversions. Let's try another. The pressure of a tire is measured as 800.4 millimeters of mercury. It says, what is this pressure in kilopascals? All right, so again, we are starting with 800.4 millimeters of mercury, so that is going to go in the beginning of my train track. And then when we're making these train tracks, we always have to cancel down and to the right. So millimeters of mercury will have to cancel with millimeters of mercury. So again, we go look up at these conversion factors that I wrote along the top, see what number goes with millimeters of mercury. That's 760. And it says, what is this pressure in kilopascals? So on top, we'll go kilopascals. And then we look and we see, which number goes with kilopascals. And we see, okay, that one's 101.3. Millimeters of mercury cancels millimeters of mercury. We can multiply our numbers on the top, divide by the bottom, and we get our answer, 106.68 kilopascals. So since these things are all equal to each other, we can use all of the conversion factors kind of interchangeably, which is really, really cool. So you're not going to end up doing a lot of multi-step conversions. It's mostly just going to be this one quick train track whenever we're doing pressure conversions. I have two more examples for you. You can try this one if you'd like. You can go ahead and, here, I'll write the conversions along the top. 1 atm is equal to 760 millimeters of mercury, is equal to 760 torr, which is equal to 101.3 kilopascal. So if you want to go ahead and pause and try this first one out, you should be able to do it based on the last two examples. All right, so here's the answer. So we're starting with 2 atmospheres, so that is going to go in the beginning of our train track, 2 atms. And we know our units always have to cancel down and to the right, so if I have atms right there, then I'm going to need to put atms down here. We look at our conversion factors, and we see what number goes with atm. We see that's a 1, so we put 1 atm down there. And then since we're trying to find torr, that's what we will put on the top. And then we see what number goes with torr, and we see, 760. So we put 760 there. So atms cancels atms. We're left with we're left with torr on the top, which is what we're trying to find. Multiply the top, divide the bottom, we get 1520 torr. So that one hopefully was really straightforward. I have one that's just a smidge trickier, which is this last example. If I can get it to come on. Whoop, hang on. There we are. So the pressure of a tire is measured as 3 atms. What is this pressure in pascals? And I put careful, this is different from kilopascals, but we know, right, these prefixes, if you'll recall, that prefix kilo, right, we've seen that before. So our little last conversion factor is that 1 kilopascal is equal to 1,000 pascals, right? Because we know this prefix kilo means 1,000. So 1 kilopascal is equal to 1,000 pascals. So we can go ahead and start with our train track. So this is about as tricky as I can make them. So we put 3 atms at the beginning of our train track. And we're trying to find pascals, so we're going to convert first to kilopascals and then use this new conversion that I've written there to convert from kilopascals into pascals. So, but again, we have to cancel atmospheres down and to the right, so we'll start there. So put atmospheres on the bottom, we look, we see the number that goes with atmospheres is 1. And then, like I said, we're going to convert this into kilopascals, then use our new conversion to convert it into pascals. So we're going to convert to kilopascals, and we look and we see the number that goes with kilopascals is 101.3. And then once we've converted to kilopascals, we can use this new conversion factor that I wrote over here. And remember, kilopascals must cancel kilopascals down and to the right. So we'll put 1 kilopascal down there and 1,000 pascals on the top. Double check that all your units are canceling. And you should be left with pascals, which is what we were trying to find in our problem. Then we can go ahead and multiply everything on the top, divide by all of the numbers on the bottom, and get our answer. And that's it for today. we did, some general properties of gases and learned how to convert between different pressures. So you've got one more lecture worksheet problem to work on for this, and that's going to give you some practice converting between different pressures.